response of an RC circuit to a single rectangle wave. Yeah. All right, so look at the problem. RC circuit, but V, the voltage function, this time is a special one. Look at, this shape. So it's called a single wave. Okay, single wave first. Then rectangle, yeah, wave. Yeah. Here you can see we can use that unit step function to model it, to write exact form of this one. Okay, yeah. All right. So let's look at the question. Find the current little I of t. Yeah, little I current. Here in this chapter we use little I. Yeah. So you will know why. Little I of t in the RC circuit in the figure if a single rectangular wave with voltage V0 is applied. Yeah. Yeah. First, let's write the equation. All right. Here, first, let's write the voltage function. Voltage function, V0. Yeah. That's the constant, V0. Okay? Never changes. Yeah. But after that, we need to use the difference of two unit step function with different shift number, A and B. Yeah, A and B. Starting from A and with B. Yeah. That difference. Yeah. Because difference after B cancel out, or 0. Okay? Before A, 0. Between, the value comes from the first term. 0 from second. Yeah, so that this shape. Yeah. All right. Now we can write the ODE. Yeah. Out. Yeah. ODE. Yeah. Little I current function R times I function plus little q charge, amount of charge in this capacitor, yeah, over C. Right. C given. Yeah. Oh, here. Yeah. All right. Here, I didn't copy it. Anyway. All right. So that little v. Yeah. So specifically, we have this representation. Yeah. All right. Next step. We need to apply Laplace transform on this equation, both sides. So we need to select the formulas. Okay. Yeah. All right. Because when we apply Laplace transform on the right-hand side function, we need to know Laplace transform of the unit step function. Yeah, this formula we need to put here. Okay, then let's apply Laplace transform. R constant, Laplace transform on little I, we get a capital I of S. Now you understand why we use little I for the current function, because capital I refers to Laplace transform. Little I, original function. Little notation, corresponding little notation, original function with variable t. Yeah. Then corresponding Laplace transform, capital. So that's the reason in this chapter. Yeah. All right. Yeah. Then here. Here, Laplace transform on integral. Yeah. We have a formula, right? Laplace transform on integral. Yeah. I didn't copy the formula. Yeah. I should copy the formula somewhere. Yeah, because Laplace transform on integral, you need to do division by S. Division by S. Okay? Capital S, the original Laplace transform, but to get integral, you need to do division by S. That's our formula. Okay, all right. Then apply the Laplace transform on the Heaviside function. Yeah, you get that. All right. Then algebra. Okay, solving for I of s, solving algebraic equation. So you get an I of s. Here I just write it in a more friendly form. Here I do another step, more friendly for our formula applications. Because when you need to apply formula, you need to make the form fit the formula well. Yeah. So that's the reason we changed that. Here, basically, the denominator s plus a constant number. S plus a. That's s plus a form. Okay? That's the reason we use this form. Yeah. The constant numerator, denominator s plus another constant, we treat as a. Yeah. Now, we can, before we write the final inverse Laplace transform, let's assume this function, this whole thing, this whole function as a capital S, capital F of S. Yeah. Then multiply this E part. E part, we know we have that Heaviside function we can use. Yeah. All right. But this F, what is the inverse Laplace transform of this capital S? We need to calculate. We need to calculate inverse of Laplace transform here. Okay? All right. Basic formula, yeah. Denominator S with a shift. Yeah. But the base formula is 1 over S. Then we do shift. Okay? Well, then we do shift. Yeah. So we use this formula, yeah, the first formula. Then, second, when we shift by A, this is our A. Okay? That is our A minus negative this number. Minus negative this number. That's the A. So you replace that little a by negative this number. Yeah? So that's this formula. Okay? So we calculate the inverse Laplace transform of capital F. Okay? All right. The capital F, so we can have the little f. Then, how to get those E part? E part. We use this formula. E function times f. Then we just use the little f and the Heaviside function product, then shift by a. Shift by this number a. Second term, shift by that number b. The difference. All right, as the final result. Okay, all right. Oh, yeah. So this slide, let me complete the remaining computation. Yeah. I just talk about our plan, okay? The previous slide, I talk about the plan. Yeah, some students still copy the previous one. Yeah, yeah. So we make our plan, okay? The next one, we execute our plan. Yeah. All right. Now let's execute our plan, okay? So all these formulas ready. We use these formulas, okay, already. Yeah. And the current state. So we have this function. We want to calculate inverse Laplace transform here. Right. First, let's calculate inverse of only the f part, capital F part. So that this big fraction. Inverse Laplace transform of that big fraction. Yeah. Numerator constant, can we take it out? Numerator constant. Yeah. Linearity property, we take the constant out to simplify it. There, denominator s plus, this is a, 1 over RC constant, we treat as that a, okay? Yeah. 1 plus, yeah, that constant, yeah. But here, look at this one, okay? The s minus a, so a corresponds to negative that fraction, this fraction, 1 over RC, okay? All right. All right, yeah. Then the next step, all right, next step, we apply this formula. This formula, two parts, the product. First, the E part. E to the AT, what's A? A from here, negative 1 over RC. Okay. So e to the negative t over RC. Yeah, that's the e part. E part, then little f. What's the little f? Little f by inverse Laplace transform is 1. Okay? Inverse Laplace transform of 1 over s. It's 1. 1 times the e function. Yeah. So you do not see 1. Yeah. Okay? Yeah. All right. This is the little f function. Yeah. Before we consider inside the bracket 2 e terms, the difference, before we consider that, we have the little f function corresponding to that capital F Laplace transform. All right? So we get a little f function ready. So the last step, final step, apply this formula. Because little f ready, so we apply this inverse Laplace transform. The first term, that A, so the here, okay, the current little I function inverse Laplace transform, then the difference of these two Laplace inverse transform. Yeah. The first one, let's write the first one. First one, look at this formula. Exactly the same format. Okay? All right. So little f, yeah, here, because we have the little f definition. Okay? Little f, then you replace t by t minus a. The second term, replace t by t minus b. Okay? Yeah. Yeah. So then the last step, because you know the little f. So you know the little f. So you just copy the little f. Yeah. Yeah. Factor that out. That's the final solution. Yeah. That's the final solution. Yeah. Yeah. Try to practice, to handle the complexity of the computation like this. Yeah. Think about if you can handle the complexity like this after a few rounds of practice. Yeah. First, you need to get familiar with all these basic formulas. All these basic formulas. Yeah. Yeah. You need a lot of experience using all these formulas. Okay? Yeah. So then practice, to get yourselves, feel comfortable doing the calculation. Here, all algebraic calculation, computation. Okay, so no derivatives, no integrals. Yeah, yeah. No integration by parts, right? Yeah, yeah, yeah. All right. Yeah, but still, I do not say it's very easy. Still, it's pretty complicated. Yeah. Yeah. All right. Yeah. So that's this question. Yeah. All right. Next, I want to go to the second special function, Dirac's delta function, another important function for engineering problem, modeling right side function of engineering problem. This one is a direct delta function. Yeah, those two special functions. But this function even more special than that Heaviside function. Heaviside function, we see the graph, so simple. So we can understand. But this one, you will see, yeah, it's hard to imagine, very hard to imagine. What is the function? What is the, picture of this function? Yeah, not that easy to understand. Yeah. All right, so let me talk about the definition of Dirac's delta function. Here, we do not direct the delta function directly. At the beginning, we define a sequence of special functions. Little f sub k, this function, of t minus a, this function equals 1 over k for t in this interval between a and a plus k, and a 0 otherwise. Look at this function. Yeah. It's a simple function. Yeah, it's a simple function. We can draw its graph like this. Let me show you. This is the graph. Okay, this is this function. The shape like a skinny rectangle. Skinny rectangle. Because later we will make k very close to 0. Later we will make k very close to 0. So you can see a very long, skinny rectangle. That's the graph of this function. But that is fk function. That is fk function. And you need to change that k. How do you change that k? You make a k approaches to 0. You make k approaches 0. That's the way you change. Okay? So what's that function? Yeah. K goes to 0. So the value 1 over k goes to infinity. What's that function? So that's why it's very hard to imagine this special function. Yeah. But this function is very useful. All right. Look at that. So here we define the delta function. Dirac's delta function. What's the delta? We make k goes to 0, the limit of fk function. That's the definition of delta function. Yeah. But the question is, does the limit exist? Does the limit exist? You make k goes to infinity by calculus. If we use calculus, the limit does not exist. The limit goes to infinity. So there is some understanding problem here. Limit does not exist. But how can you define a function using the limit, but that limit does not exist? How can you do that? The delta function. That's the definition of delta function. So that's the reason this function is so special. Yeah. All right. So it's called a Dirac delta function. Yeah. Another name, unit impulse function. Another unit function. Unit impulse function. Impulse. You can see the shape looks like impulse, right? The shape like impulse. Okay? Yeah. So you can see we use this function to model the real world impulse phenomenon. Real world, lot of impulse actions, right? Yeah. How do you model those impulse phenomena? This function. That's why this function is useful. The impulse phenomenon. All right? Yeah. Yeah. Why unit? Because the area equals 1, that means the unit. Okay? It's area. Area is fixed. The area is fixed, equals 1. So that's the reason it's called a unit. Unit impulse function. Okay. All right. Now this delta of t minus a, we shift a position. Yeah. Original delta function is at 0. Delta of t is, the a equals 0. Yeah. But we shift to general location a. Yeah. After that, the first thing we know, this is not a function, right? Based on our function definition, definitely we cannot call this one a regular function. Okay? Yeah. Then people call it a different name. Yeah. Although here we say direct function, yeah, but people call a different name, called a generalized function. It's not a regular function. It is a generalized function. Okay? Yeah. The function definition here is modified. We cannot use the original function definition. Yeah. So we generalize it. Okay? We allow this mathematical object to exist. We allow it. Yeah. Yeah. At the beginning, most people cannot accept this concept. Yeah. Too radical at the beginning. How can you accept it? But if you accept this concept, when you use it to solve problem, it's very powerful. So now that's the reason, especially for engineering people. Very powerful for problem solving. Yeah, so then, everyone has to accept it. Yeah. This, radical concept. All right, yeah. So the definition, delta of t minus a, the definition, its value is infinity at t equals a. How can you define function using infinity as its value, right? You cannot, yeah. But here we have to generalize our usual function understanding. Yeah. It's not usual, yeah. It's special, okay? Yeah. So 0 otherwise, that's its value, okay? Then it has a main property, its integral, delta of t minus a integral from 0 to infinity is constant 1. It's a unit. That's the area, right? That's how we calculate the area covered by this function, the unit area. Okay? So that's this important property. Okay? So the delta function, now our understanding is like this. Yeah. It's a generalized function. Okay? So we allow it. Yeah. All right. Then modeling the phenomenon. Yeah. Because after you accept it, then we need to use this function to modify, to model the real world phenomenon. Okay? So what kind of phenomenon? Here, I'll give you a few examples. Yeah. Impulse phenomenon. An airplane making a hard landing. Is that some impulse? Yeah. Big hit. Yeah. Strong big hit in a short period of time. Yeah. The main reason is it occurs in a short period of time. That's our modeling function, right? Short period of time. A big hit, big force. Yeah. Big force occurs in a short period of time. How do you model it, right? Yeah. So we use this function to model it. So you can see, yeah. Very reasonable, right? Yeah, very reasonable. Yeah. Another one, a mechanical system being hit by a hammer blow. Yeah. Another impulse example. Okay, another impulse example. The third one, a ship being hit by a single high wave. Yeah. Just so you can, imagine many such examples in the real world. Yeah. Here we use this function to model it. Okay. All right. Impulse of a force. So now, the reason we use this special function to model impulse of a force. If you see, right-hand side of your ODE is an impulse of a force, then you need to use this function. Actions of forces, mechanical or electrical. Electrical, you may have that, right? Impulse of, voltage, current, right? Impulse, etc. are applied over short intervals of time. Yeah. So that's the, reason important. So here you can think about, if you do not use Laplace transform, if you use our chapter 2 method, how can you solve problems modeled by this function? Very hard, right? Yeah, Laplace transform. Now you can appreciate the power of Laplace transform. Yeah. So that's why I emphasize so important. Okay? Yeah. All right, let's continue. Yeah. Delta function, a powerful tool. Yeah. Now, we want to use the power of this tool, special tool. Yeah. Properties. Shifting property. Yeah. First, shifting. Yeah. This property, yeah. Very useful. Now, shifting, what's that? Yeah. You have a g function. You know, arbitrary given g function, but this g function must be a continuous function. Yeah. Must be a continuous function. Then we have this property. So you take integral of the product of g function and a delta function, but delta function shift to the position A, yeah, the center at the position A, okay? The center at the position A. Then, if you take integral, the result, g function value evaluated at the A point. That's a nice property of this function, delta function. Nice property. Okay? Yeah. Here I can prove it. Proof. Very simple. Yeah. Just one line proof. Yeah. Let me explain the proof. Otherwise, you'll feel how to understand. So I want to convince you it's correct. Yeah. All right. Let's consider, because delta, we cannot do calculation on delta, right? It's too hard. So we go back to the original definition. When we describe delta, we go back to the fk function. Then we make k goes to 0 to, approximate, to get delta. Yeah, all right. So here, let's apply fk function here. Fk, yeah, here we use the function value like that. Okay? We take integral outside this little interval from a to a plus k, all 0. So that integral becomes 0 outside that interval, right? Yeah. So that integral we only need to consider between, inside this small interval, a to a plus k. So we only do that integral. In that interval, fk function equals 1 over k, constant. Constant. Yeah. So we can take it out. Okay? Take it out. But then we need to use the continuous property of g function. G is a continuous. Think about in a short, very small short interval, the continuous function value, can we approximate continuous function value using g of a? Yeah? It's just 1 point. Because in the short, other places, the value is slightly different, very close to this one. Okay? If we take the limit, then it's this value. So we can, use g of a to approximate g function value, but this approximation is close to 0 when we take the limit. After we take limit, extremely close to 0 and hit that point. That's the continuous function property. Okay? So g of a there, yeah, so that you calculate the, because the difference is k. K times 1 over k, it's 1. 1 times g of a, g of a. So that's the reason you have this value. Yeah, continuous. But if not continuous, then you cannot have this shifting property. Yeah. So be careful. Must be a continuous function here. Okay? Yeah. All right. Yeah. Then we can do Laplace transform. Yeah. Now we do Laplace transform so we can calculate our real-world application questions. Laplace transform of the delta function at t minus a, this function, equals e function, e to the negative as. So simple. Yeah. Laplace transform, this is just e function. How good it is. See? Yeah. Not bad. Yeah. It looks, this function is bad, right? This function, when you describe it, the behavior is so hard to control. But the Laplace transform so good. See? Right? Yeah? All right. Yeah. The proof here, let me describe proof a little bit. Yeah. Still, we use little fk. Fk, this time, we use the Heaviside function to write it. Yeah, I mean, based on that shape, we can use Heaviside function to represent it. Okay, all right. Then Laplace transform, can we do it? Yeah, because k goes to infinity. Sorry, not infinity. K goes to 0. We can calculate that limit later. How about that? First, let's apply Laplace transform. After we get a formula, then we let k goes to 0 to calculate. Okay? All right. Yeah. Yeah. So here we need to use this Laplace transform of Heaviside function. Use this formula. Okay? Yeah. Over S. Yeah. Over S. All right. Yeah. Then take Laplace transform on Fk, 1 over Ks, the bracket, because here we have two terms. Yeah. Two terms. So you have the difference of these two e function. Okay, all right? Yeah. Then factor this e to the negative as out. Then this fraction, look at this fraction. This fraction, can you imagine you can take a limit making k goes to 0? How about that? Take limit when k goes to 0. Yeah, you can use L'Hopital's rule. L'Hopital's rule here. Okay? Yeah, yeah, yeah. But here I want to use another way. Yeah. Other than L'Hopital's rule. Yeah. Yeah. Our textbook said use L'Hopital's rule. But here there is another rule. Another method we can see easily. The answer is the limit is 1. The limit of this fraction when k goes to 0 is 1. We can use the power series expansion of e function. Right? Power series expansion of e function. You can easily see the limit is 1. Okay? Yeah. Let me just show you quickly. Yeah. Power series. But here, e to the negative kx, right? E to the negative kx. Ks equals 1 plus negative ks plus ks squared over 2 dot dot dot. Okay? Yeah, that's enough. All right. Then minus 1 minus that term. Yeah. Look at the 1 minus this e. Can you get ks plus ks? Yeah, because minus negative plus, but minus ks squared over 2 over ks. Okay? Yeah. But those terms approaches to 0, ks cancel out 1, right? Yeah. Ks cancel out. Yeah. So that's why you use the power series expansion of e function. You can also see the limit of this fraction when k goes to 0 also 1. So then the answer is, yeah, the delta function. You go back from fk to delta function. Its Laplace transform is e to the negative as. Yeah. Yeah. Then you can apply this formula, right? So when you solve ODEs, you just apply this formula directly. Yeah. All right. Let me show you one example. So then we start our recovery session number 1. Yeah. All right. Yeah. Example number 4. Yeah. One example. Mass spring system under a square wave. We're familiar with mass spring system. Okay? Yeah. Second order ODE. Yeah. But here we need to change the, driving force. The driving force is a square wave driving force. Yeah. So what's that? This response. Yeah. All right. So this is the driving force. It's called a square wave. Okay? Square. Single square wave. All right? Yeah. This is the solution function. Yeah. So here you just ignore. This is the solution function. Yeah. So this is the force function. Okay, force function. All right. ODE y double prime plus 3y prime plus 2y equals the R function. We use the difference of the Heaviside function to describe it. Yeah. Here, not delta. Here we use the Heaviside function. Okay. All right. Initial condition. Yeah. Then solution. You take Laplace transform. First derivative, second derivative formula, initial condition. Because based on initial condition, all these terms all gone, right? So in f of 0 equals 0. So all these terms all gone. Initial condition 0. Okay. Yeah. Then we have Laplace transform y double prime equals s squared times capital Y. Okay. Laplace transform of y prime s times capital Y. Okay. Yeah. So then you put together. Yeah. All right. So here the right hand side Laplace transform, we use this formula. Yeah. The formula. So now both sides. Left hand side s squared capital Y plus 3s capital Y plus 2 capital Y. Right hand side, that formula. Apply it twice. First time, second time. E to the negative s minus e to the negative 2s. Okay? So common denominator over s. Yeah. Then we solve this algebraic equation for capital Y. Capital Y equals this expression. Yeah. This expression, the e terms, we know e terms, the Heaviside inverse, yeah, we can handle by the Heaviside inverse Laplace transform. So first we only need to calculate inverse Laplace transform without e terms. Yeah, we use one first. Then we consider adding e terms back in the numerators. Okay? All right. Now we want to split. Yeah. Some of you may feel you need to use a partial fraction way to write decomposition, right? Partial fraction. Yeah. Yeah, although you can use partial fraction, yeah, but here I can use my eye to split in this way. First fraction 1 over denominator s plus 1. Second s plus 1 times s plus 2. Common, so the difference s plus 2 minus s. You have 2 numerator, right? But we need to multiply 1/2 to make that 2. Add a numerator to 1. Yeah. In this way, you can avoid partial fraction step. But not done yet, because you can split furthermore. Denominator still product, not the simplest case. We still want to split 1 over s times s plus 1, the difference of these two fractions, to make it simpler, to make each fraction simpler. Similarly, the second one, we split the difference of that two simpler fractions. Okay? Then, write fs together, we get that expression. Okay? Yeah. Then inverse each one, the denominator s by a shift. So what's that s? Yeah. Here I use a new slide to show you. Yeah. We want to calculate the inverse Laplace transform. Yeah. Yeah. So that's in that way. But we need to have the inverse Laplace transform of 1 over s. We have a basic formula. Our formula 1. Inverse 1 over s, that's 1. That's 1. Okay? Shift by 1, we have the shift formula. Shift minus a, negative 1, so multiply the e term. Okay? All right. So then 1/2 times 1, this is 1. Okay? The shift part, e to the negative t times 1, also 1. Then 1/2 times e to the negative 2t, a equals negative 2 times another 1. Yeah. So that's the answer for that little ft. Yeah. Yeah. But not done yet, the last step. The u Heaviside, or that e term. So remember, we have this numerator 2 e terms. We need to use the Heaviside, this function. Yeah. Each e term, we write that expression. Each e term, yeah, split separately. Each e term, f of u, shift by 1, second shift by 2, that difference, that's our y. Little f, we know this is little f. Okay? Yeah. So here, I do not need to write explicitly. Okay? Yeah. At this point, although we can write another step, but we're almost there. We're almost there. Yeah.
Just the right side of the equation.
Yeah, just, yeah. Oh, yeah, little f, the solution of the whole equation. This y, that's the solution. Yeah. Solution function. Final solution function. Yeah. Satisfy initial condition. Yeah. All right. Yeah. Now you take a piece of paper. Yeah. But do not use any materials.